Hey, do you like multiplication?
Maybe. Is that okay?
Yeah, it's cool. I like math.
Cool.
Hey math lovers, let's go over 8.4 normal distributions. What's our learning targets? The standards for mathematical content. Students will use the mean and standard deviation of a data set to fit it to a normal distribution and estimate population percentages. Recognize that there are data sets for which such a procedure is not appropriate. Use calculator spreadsheets and tables to estimate areas under the normal curve. And SIC6, evaluate reports based on the data. How can you meet this standard? I can use the mean and standard deviation to analyze normal distribution data. By using technology. Alright, let's go ahead and go over this warm-up. And you go ahead and try that. One tip I want to tell you is that standard deviation for the population is this symbol, which we learned previously was called sigma. It's just standard deviation. Variance is just taking the, that's just abbreviation, variance is taking the standard deviation and just squaring it. Okay, go ahead and try that and then press play and then we'll do it together. Alright, it tells us to find the variance and standard deviation for each set of data, round to the nearest tenth if necessary. I'm going to plug in those three numbers into my graphing calculator. I'm using graphing calc 83 there. And I'm going to go to Stat, Edit, and go to the very top of your list, or you can just click there if you have a touchscreen tablet. Clear, Enter, Clear, Enter. And then we're just going to input those numbers. 8, 2, whoops. Can make a mistake like I do, that's okay. Enter, 2, Enter, 10, Enter, 6, 9. And then while I'm at it, I'm just going to do the other ones as well. 78, 78, 95, 87, and 62. And then list 3 over here, I got 4.5, 2.5, 4.5, and 2.5. Okay, so it does have 5 numbers in the first list, 5 numbers in the second list, and 4 numbers in the third list. So let's get out of here. Second mode, or to quit. And then I'm going to press Stat, Calc, 1 bar stats. Remember, if you just press Enter here, the default is just list 1. Okay, here I have 2.8. Looks like ox, but it's not. That is my 1 bar stats there for my first list. Okay, what you can do is you can just take that number, 2.8, I don't know, round it to the nearest 100, and then square it. It's over there, top left of the 7. And this gets me approximately 8. So here my variance is going to be 8 and my standard deviation 2.8. Okay, so do the same thing for the other one. Stat, Calc, 1 bar stats, and now I need to put list 2 in there. So there's 2 ways to get there. You can press second stat, or I'm just going to press second number 2. You don't need to close parentheses. And there I have a standard deviation. Looks like, again, ox right above the n is 11.00, so 11. And then if I take that number and square it, take this number 11.009 and you square it, you get approximately 121.2. And I just took that number 11.0, because remember it was like 0.9, and that number is less than between 0 and 5, so that number stays. So I don't really need those numbers. And the last one, stat, calc, 1-bar stats. I need list 3. Let's do the second method. Second, stat, list 3. Enter. Okay, my standard deviation there is 1, and if you take 1 and you square it, it's just what? 1. So let's go back out here. Oops, I don't like using that color. Okay. Which of these numbers were clustered more around the mean? So the word mean, let me draw. This is our ghost, the normal curve. We're going to learn that today. But mean is a measure of center. It actually goes here in the middle. So where is that data close around the middle? Well, remember, standard deviation and variance are measures of spread. Measure of spread. So if it's a small number, such as 1 and 2.8, they're going to be around the middle. But if they are a big number, you like that color? Like 11, then they're really far spread out. Okay, little spread around the center like jam, strawberry preserves, or if it's a large spread, it's really spread out. So which of the sets were more clustered around the mean, which means they would have a small spread? I would say in that one, number 3 had the smallest one. So we'll warm up number 3. And then which one was more dispersed? That one's just more spread, widely going left and right. That would have been warm up problem number what? 2 had the largest one. Okay, so now this question number 5 tells me to create a dot plot. And what I'm going to do is look at the range. I'm going to look at the largest number and the smallest number. I see it's like pretty much like 10, and I see a 5. So what I'm going to do is I'll put 5, 6, 7, do my best to equally distribute them, 9, and 10. And a dot plot just basically means we're going to put a dot. And as you do that, go ahead and put a check mark so you don't forget where you put it. 6.2, 7.6, there's a 5, 7.1, 9.4. And it is important to have the same size of a dot. 6.6, 8.3, 7.8, 5.7, 9.9, 6.1, and 7.3. Okay, so here is my dot plot. And that didn't give me great results. So another way of creating another dot plot is putting them into bins. Putting them into bins. And this time, I'm going to say all the numbers in here are between 5 to 5.9. And I'll say 6 to 6.9. And 7 through 7.9. 8 to 8.9. 9 to 9.9. And I'm going to do it again, so 6.2. But I'm going to just put it above the tick mark this time. 7.6 is in this bin, like a drawer, kind of like, you know, you put away your clothes. 7.1. See what I did there? 9.4. 6.6. 8.3. 7.8. 5.7. 9.9, and this is giving me a better visualization. You're going to see this 6.1 and 7.3. And what we like to do is then draw mountains over these peaks and valleys of the mountain. And that looks a little bit better on my data. Okay, let's try the same. Let's try the same. Do some magic. Watch this. Say the words. Magic. Magic. And let's go ahead and this one, let's go ahead and make a histogram. And the histogram is the same idea, but now we can just indicate it. There's like 1, there's 2, 3, and 4. So there was 2 over here. Do you see that? 1, 2. And then in the 6.9 bin, there are 3. And then there's 4 over here. And then 1. And then the next bin there was 2. I want to show you guys this. This is really cool magic. Let's see if I can get it. I think I was able to grab it. Let's see. Pretty close. Do you see what I was trying to do here? What I was trying to show you is that basically the distributions, the graphs, are pretty much the same for a dot plot or a histogram. Okay, that is our review. All right, the normal distribution is and we're here doing the launch. The normal distribution is a continuous, symmetric, is what goes into your fill in the blank, symmetric, bell-shaped distribution of a random variable. Now let's get this into real life. For each animal species, gestation time, gestation just basically means pregnancy. So in blank number 2 goes pregnancy. It can be described as a normal distribution. All right, what are my 3 animals here? I have a pig, hamster, and a dog, which is like a specific one. It's a beagle. Beagle? Beagle. Different animals carry their young in the womb for different amounts of time. The average gestation or pregnancy time, how long the baby's inside the animal, for a species is usually related to their body size. The gestation time for each species can be described by a normal distribution. Our normal distribution is a continuous symmetric bell-shaped distribution of a random variable. All right, there are our 3 babies. This is a normal curve. It looks like a bell, kind of. I don't know, that's what they call it. About 60% of young are born within 1 standard deviation of the mean time, and 95% of the young are born within 2 standard deviations of the time, right? And the baby could come in the middle here, and the mean just being the average. So a baby can come late or a baby can come early. You know, most of my babies were born early. Here is the mean time. So on average, a hamster will give birth every, when they're pregnant, will come in 16 days. And then the standard deviation basically means, you come up to one other, it will take 3 hours more or 3 hours less. And then most of that data is within 3 hours, right? Beagle holds a baby 65 days and their standard deviation is 5 hours. And then a pig, which is a lot bigger, you guys can see the size, average is 116 days versus 2 days. Long and short? Shortest. Gestation period for an animal is a possum, 11 days, and an elephant, 645 days. And then there, blanket number 4, the average length of a human gestation is 267 days. I did not know that, even though I have 6 kids. I think it just means that it's like 9 months. All right, let's go ahead and move on to our exploring the probability distributions. All right, so we said the answers were symmetric. Symmetric is like your face, and you cut it in half. A heart is symmetric. If you put a mirror right there, cuts it in half. Does it make sense? And then we said for each animal species gestation time, which is basically another word for pregnancy. Did I spell that right? And the 3 animals shown were a hamster, pig, and a dog, which was a beagle, and 267. All right. All right, let's do some exploring here. And I'll just give you the first one to help you. If we roll 2 dice, it has the numbers, it has the numbers 1 to 6, right? So if I do something like this, and the sum just adds them together, then I get a 4. So can you list them all out and then answer questions 2 to 4? Click on the word simulator here, and you're going to do something, draw a picture, and then we'll fill out the rest there. All right, let's go over this simulator. Simulator is just a way of computer, instead of me rolling the dice many times. So again, I sum here, that would be 2. So hopefully you made a prediction, all the different sums, and which one do you think is more likely. Are they all likely to be rolled? And if not, predict which number will come up the most. Let's go ahead and press this 1 a couple of times. Okay, so 4 plus 4 is 8, so it's making a histogram here. Just press it a couple times, 11. And let's press 10 a couple of times. Now it's rolling 10 dice at a time, so now next 10 dice would be 36, and they just add them to the different bins, right? So 9, that one went in there. And what do you guys notice is happening? Let's do 100 a couple of times. And then you can press 10,000 a couple of times. Boom, 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 boom. I don't know, let's go crazy. Okay, so let's just draw that on our graph here. Okay, so hopefully you would have said that the different numbers that can be added up are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. You could have made a prediction, I don't know. Maybe thought 6 was the most popular number. Well, whoops. Will these all come up? Maybe you said yes, maybe you said no. I'm not sure which one you wrote. But if you wrote, yeah, no, which one do you think came out most? Maybe you're like 8. And then we did the simulation there, and let's go ahead and draw ours. If I can. I don't have the numbers, they were too big. But there was nothing rolled in the ones. And it kind of just kind of looks like there's these staircases, this histogram. To review the graph distribution that you drew above, this is called our experimental probability. Why? Because we did something. We do. While this one is actually, there's actually 36 outcomes. So a 7, let's see, 7 can we come up with how many ways? I think it's, let's find out, double check. So you can have a 1 and a 6, or 6 and a 1. You can do 2 and 5, or 5 and 2. You can have 3 and 4, or 4 and 3. And so there are, that would be 1, 2, 3, 4, 5, 6. And there's 36 outcomes, so you get 1 6, which is like 17%. So that one, this one is called our theoretical. Should have came up 16% of the time.
And math is all that is surrounding you. Math is so much more than 2 plus 2. You can understand it. Take that number and divide it. Math was made for me and you.